Thanks so much for organizing this event, for having us. It's great to present our project called WarpDrive today. WarpDrive is an open source framework that lets you do extremely fast end-to-end deep multi-agent reinforcement learning on a GPU. This is joint work with Tian, Sunil, and myself. Tian and Sunil are here as well. So I'd like to start off with a brief introduction of why multi-agent reinforcement learning is important, and then Tian and Sunil will walk you through all the details and all the cool performance results that we have with our framework. Next slide. So to start off, WarpDrive can be used to do multi-agent reinforcement learning. This is a frontier for AI research, so maybe you're familiar with systems like AlphaGo, Dota 2 bots made by OpenAI. All these AI agents have shown that they can master really complicated decision-making problems using reinforcement learning. And in this area of research, we're asking the question of how you can use that technology to study problems where there's more than one AI agent in the world. So in our own research, we focus on designing economic policies in a virtual economy. In the left, you can see this animation in which there's four agents, AI agents that are working and are making virtual money. And in our research, we asked, if you have such a virtual economy, can you then design better economic policies using reinforcement learning? And the reason this is multi-agent is that both the government that sets economic policies as well as the AI agents that are working for money are all controlled by reinforcement learning agents. And we've shown that using this research that you can find economic policies that outperform classic economic benchmarks in terms of social welfare. But there are more applications beyond just economics. You can also think about robotics. So if you can imagine a factory in which there are multiple arms that are working along an assembly line, so these arms are cooperating to make some sort of product, then you can imagine that each arm is driven by a reinforcement learning agent. And all those agents would then have to cooperate in some way to make a product as efficiently as possible, for instance. So there are a number of startups that are actually working on this right now and might also even be using reinforcement learning. And a third example of multi-agent learning is in human-computer interactions. So you can imagine that in the future, people are interacting with robots, and even today we're talking to chatbots. If you call your bank, or if you try to get help from your bank, we're already interacting with computers. And so it's really important to understand how computers would respond to all kinds of different human questions and answers and follow-up questions and so on. And typically there's just not enough data to really go and collect a lot of data in the real world with real people. And you can imagine that an AI could actually stand in for a human to train the computer as fast as possible. And again, that's an example of multi-agent learning. Next slide, please. Now, hopefully I've convinced you that there's a lot of interesting applications where multi-agent reinforcement learning will be very relevant and important. But at the same time, the current systems that exist for reinforcement learning are still quite slow when you try to apply them to multi-agent problems. In short, multi-agent reinforcement learning requires a whole new skill of machine learning engineering. And in this talk, we'll talk about how WarpDrive can help with that and really shows remarkable performance improvements, in particular for the multi-agent setting. So I'll hand it over to Sunil, who's going to demonstrate all of this next.
Thanks, Stephan. So before we introduce WarpDrive, we shall briefly go over why the current distributed RL architectures underperform, especially in the presence of many agents. Modern deep RL implementations, they perform simulation and learning on different machines. Here we have the architecture block diagram for two very recently developed RL frameworks. There's Seed RL on the left and Mava on the right, and other recent frameworks are quite similar. Essentially, there are many distributed actors and learners operating in tandem. The actors continuously step through the environment using the actions provided by the learner to generate rollouts. And the learners use the rollouts to then optimize the policy models. While these architectures are highly scalable, they suffer from several issues. First, there's a lot of communication between the actors and the learners at every time step, which makes training extremely slow. In particular, when the number of actors is large, or when the observation space itself is large, there's a lot of back and forth data transfer between these devices. As the number of agents grow, running the simulation or the rollout itself can become a bottleneck because you're looping across multiple agents. And while it's often possible to parallelize operations across agents, the rollout time only increases and gets worse as the number of agents increases. This hardware setup is non-trivial, and that's because we need to set up a cluster of nodes with multiple processors, and also it means there's a lot of power utilization. The compute requirements for the actors and learners are imbalanced, which also leads to poor utilization. Indeed, generating rollouts and batch training, they're very different tasks. So calibrating the optimal ratio of actors to learners gets tedious. With all these reasons, it remains challenging to apply RL, especially in the context of complex simulations involving multiple agents. And we've seen in our own experiences that training can take days or even weeks to finish. So as such, distributed RL poses unique challenges. So there's been recent work along the lines of doing end-to-end reinforcement learning on a single device. In particular, we have Brax and NVIDIA's very own Zheng that both focus on running 3D rigid body physics simulations, such as robotic control problems on a single GPU. These frameworks, however, just focus on one agent or single agent simulations. Also, Brax builds on principles of functional programming, which is difficult to apply to multi-agent systems because multi-agent systems have complex state representations, and hence there's always the need to use graph-based logic or complex data structures to model the agent's interactions. So we built WarpDrive, a framework to perform extremely fast multi-agent RL on a single GPU. And WarpDrive is built on the following design principles. All the RL workflow, including rollouts, data production, and training, should be performed within one or a single GPU. We update all the data in place on the GPU, so we null out the data transfer cost between the CPU and the GPU, or the actors and the learners. We use imperative and stateful code to build complex multi-agent RL simulation logic with interacting agents. We maintain a granular control over how each GPU block or thread maps to individual agents and environments, and we maximally parallelize the operations within. Lastly, we provide an easy interface to develop new environments and training algorithms. And each part of the RL pipeline should be separately testable. So as such, WarpDrive is a flexible and lightweight framework for multi-agent RL on a GPU. It's implemented in Python. It's integrated with PyTorch for training, and it uses a CUDA backend. This is very advantageous in that users can utilize the full feature set of CUDA programming, including the GPU's parallel computation elements, making it convenient to implement even complex multi-agent simulations. Some of the key features and benefits of WarpDrive are that it avoids the back and forth data copying between the actors and the learners. All the data is copied just once and in the very beginning of training, and the subsequent data updates happen on the GPU itself and in place. WarpDrive harnesses the parallelization capacities of the GPU to run simulations with thousands of agents and thousands of environment replicas in parallel. And essentially, this means that it can train on really large batches of experience. In all, WarpDrive can run millions of RL steps per second and train in just a few hours. And this is over 100 times faster than CPU-based architectures. WarpDrive is not only useful for running environment simulation on a GPU, but it also provides an end-to-end pipeline for extremely fast multi-agent RL. It currently implements several quality of life tools for RL training, such as the RL learning algorithms themselves. In our current version, we have the A to C algorithm, which is the advantage arithmetic, and PPO, which stands for proximal policy optimization. WarpDrive also provides support for logging the training metrics, loading and saving model checkpoints along training, and it also provides support for generating rollouts on the GPU. And as we will show later in this talk, WarpDrive also makes it easy to integrate custom or your own Python gym-styled RL environments with just a couple of augmentations to the code. In fact, users only need to build a CUDA-C version of the environment step function. And once that is performed, WarpDrive provides an environment consistency checker to test the equivalence between the Python and the CUDA functions. And it also provides an environment wrapper to handle all the low-level logic and helps for automatically running and training simulations on the GPU or CPU. So next we'll talk about WarpDrive's benchmarks. And our results show that WarpDrive scales linearly to thousands of environments and agents and yields orders of magnitude faster RL compared to CPU-based implementations. So we use 3 environments in all to benchmark WarpDrive's performance. There are 2 versions of the game of tag and a more complex COVID-19 economic simulation. The tag game is depicted on the left, where we have a square with many agents. The pink colored agents are the taggers, and the blue colored agents, the runners. In this multi-agent environment, all the agents can move around on that square 2D grid in a continuous fashion. And in terms of the action space itself, each agent can choose different levels of 2 types of actions. One is acceleration and the other is turn. And the motions of the particles, they follow classical mechanics. So the taggers here, or the pink dots, are they attempt to catch the runners, the blue dots, and the runners, well, the runners try not to get caught. And in this particular depiction, agents start in positions arranged like the letters AI, and then the agents keep running around. The taggers start chasing the runners thereafter, and you can see the environment evolve over time for a sample policy. On the right, we have the COVID-19 economic simulation, which is a more complex environment. It is based on a model based using the real-world data amidst the COVID-19 pandemic, and it models the health and economic dynamics of the US during the pandemic. The simulation has 52 agents in all, 51 for every US state and the Washington, D.C., and 1 agent for the federal government. The state governments here, in this case, decide how stringent they ought to be in terms of opening and closing down the economy, while the federal government provides subsidies to individuals in the states. And actions taken by all these types of agents trade off health and economic outcomes, such as deaths, unemployment, and GDP. So as such, this makes for a complex and unstable 2-level reinforcement learning problem. First, we'll measure WarpDrive's performance as we scale up the number of environments. For this plot here, we compare the throughput on the y-axis. Throughput also is the environment steps per second, and the x-axis has the number of parallel environments running on the GPU. Now, there are 2 lines here, red one pertaining to the rollouts alone, and the green one for the total throughput, which is rollout plus training. We see that WarpDrive achieves nearly perfect or a linear parallelism as we scale up the number of environments. In other words, we can launch experiments with n environment replicas all in parallel on the GPU, and we can also scale up the throughput compared to a single environment case by the factor of n. And this is because each environment replica runs on a separate block of itself on the GPU. So this helps us obtain millions of RL steps per second as we scale up to thousands of environments. For some concrete numbers, when using 2000 tag environments, each with 5 agents, we hit about 10 million rollout steps per second and about 2 million end-to-end steps per second, including training. Also, each agent in the multi-agent simulation runs in parallel using its own GPU thread. So as we scale up the number of agents to 1,000, we still achieve about 500,000 end-to-end iterations per second. And we want to stress here that increasing the number of agents by a factor of 200, going from 5 to 1,000, only resulted in a 50% loss in throughput. WarpDrive also provides a sampler class for sampling actions in order to step through the environment. And this runs in parallel on each agent thread, and this contributes to the overall faster training as well. So compared to sampling utilities from popular libraries such as PyTorch, WarpDrive, shown here using the pink line, achieves almost a 4 times higher sampling throughput. With 2,000 parallel environments and 5 agents for the tag environment, WarpDrive can produce about 18 million action samples per agent per second. And this number remains the same even when you scale up to 1,000 agents, since the sampling is also running at the agent thread level. Next, we compare the rollout throughput performance as we scale up to more agents in the simulation environment. So for this plot, again, we consider the throughput on the y-axis. We only consider one environment replica, and we compare the performance of WarpDrive on the GPU versus a CPU counterpart. The x-axis here shows the number of agents in the simulation. And as the number of agents increases, you can see there's a clear separation of the two lines, and there is increasing benefits of running the simulation on the GPU. Concretely, for this tag environment that we ran, with 1,000 agents, WarpDrive achieved speed gains of up to 500x. And in this figure, we also have two sub-figures, partial observations on the left and full observations on the right. The difference here being how much of the world is actually observable to the agents, but the trend is similar in both cases. With the partial agent observation case, we can see that WarpDrive also achieves nearly perfect parallelism, as the pink line is very flat. So the performance gains seen so far in a tag environment also hold when we move to more complex environments, such as the COVID-19 economic simulation. So for this plot here, we're comparing the throughput across different timing categories. And we're comparing for a 16 CPU node on GCP against WarpDrive on an A100 GPU. Overall, in total, WarpDrive achieves 24x throughput gain. The environment rollout itself is 24 times faster. There's no data transfer cost associated on the GPU, like we mentioned before. And the training group is 30 times faster. And all these put together lead to an overall 24 times gain in the total throughput. And all of these results are obtained with just using 60 environment replicas or 60 thread blocks on the GPU. Finally, WarpDrive can also scale up to many more environments on the GPU. So we used just 60 thread blocks in our previous result, but you can add many more thread blocks on the GPU and simulate parallel environments within. And you can see that as we scale from 1 to 1,000 environments, the throughput increases almost linearly, even for complex environments such as the COVID economic simulation. The CPU machine, however, cannot scale to so many environments. So this means that we can outperform the CPU by much more than the factor of 24x we saw before, which was using the 60 parallel environments. So next, we'll do a demo of how WarpDrive can be used to train an environment end-to-end with just 4 easy steps and a few lines of code. For the sake of exposition, again, we consider the tag game. So here is a depiction of the tag game again, with the 5 taggers in pink and 100 runners in blue. Before training, you can see all the agents are moving around randomly, and just a few runners get tagged in the process. Now we'll switch to a Jupyter Notebook demo on which we'll show how to perform really fast end-to-end RL training using WarpDrive. This notebook is also available on our open source repository in case anybody is interested. I'm going to display it now. Sorry, just want to make sure that people can hear the audio on this correctly. If not, I can walk through as we go through the demo. Just wanted to clarify.
So I can hear you speaking now, but I can't hear the audio that's playing.
Oh, I see. Okay. In that case, I'll probably just do this and I'll do a voiceover on what's happening here so that people get an idea. So this is a notebook that runs end-to-end RL training. And essentially this notebook, what we do is we start off by defining a few environment settings that we need to define, environment, policy, and trainer settings that we need to specify to run the end-to-end training. So for there are two types of agents here, the taggers and runners. So we have the two different policy settings here. For tagger and runner, we both have fully connected networks here with two layers of 256 dimensions each. And note that with WarpDrive, you can define as many models or as many policies that you want to train on. In the case of tag, we have runner and tagger, but you can add many more different types of agents and train different policies for each agent. Or you could also combine the two agents into one, let's say a shared common agent, and you can train them together with the same policy. There's also some settings we specify for the model saving. The end-to-end training now can be performed just using 4 steps. In the very first step, we create what is called as the environment object via WarpDrive's environment wrapper. So we use the tag continuous environment object and we wrap it with the environment wrapper. One of the key parameters we need to provide is use CUDA equals true, and setting this to true tells the WarpDrive and the GPU know that it has to run on the GPU. So behind the scenes, WarpDrive does a lot of initialization and pushes a lot of basic data arrays to be there on the GPU, which include, for example, the log mask or the array containing done flags or the array containing timestamps for all the different environments. And all these are pushed to the GPU at the very first time step. and you need this when the environment is set up so that it can be trained later. So next, we just have a dictionary, essentially, called the policy tag to agent ID map, which maps the policy name to agent IDs. Here we have two different kinds of agents, the taggers and the runners. And this dictionary is basically just mapping the taggers in the environment to use the tagger policy and the runners in the environment to use the runner policy. For step 3, we create the trainer object itself. And this is something that, again, WarpDrive provides out of the box. We just need to invoke this trainer class and pass in the environment wrapper, the run config, and the policy tag to agent ID map as arguments to this trainer. Finally, we create and push data placeholders to the GPU. This is a utility function which, when run for the environment that we have, it adds the environment space, it adds the observation space and the action space. And it also pushes a lot of data that are required for the GPU run to happen. And you can see variables such as lock x, lock y, which essentially are the x and y locations of all the agents. There is the agent speed, direction, and so on. And along with these arrays that are pushed, also note that there are arrays with the same name, but with a underscore at reset suffix to them. And these are essentially the values of lock x here, for example, which need to be initialized after every array reset or after every environment reset. And along with the data that's pushed to the GPU, we also need to push the necessary observations, sampled action arrays, the rewards, and the dones. And all of these are essential for training. So once we set up the environment using the environment wrapper, we have the trainer object, and we have performed these data pushes to the GPU. The only thing remaining is to run or invoke trainer.train. Once we invoke this function, training happens on the GPU. And as training happens, we have the functionalities to save the model checkpoints or even load them if required at any time. And the sort of performance stats and training metrics printed out that are required to understand how well training is happening as we are running it on the GPU. One of the numbers that we're interested in terms of benchmarks, especially, is this the mean steps per second. And we use 5 environment replicas, and here we're hitting about 1,500 steps per second. And you can also see there's also other things logged here, like loss function values, the rewards, advantages, and also action-related numbers, statistics. So we can now go back and we use 5 blocks of the GPU before, and these are all running in parallel on separate GPU thread blocks. So we can essentially even scale this up. So let's make 5 to 50. So we're making it 10x, and then we restart and run everything. And with this, what happens essentially is you're going to scale up the training batch size because you're going to have 10x the number of environments. So we essentially gathered 10x the number of rollouts. And you can see trainings running with these 50 environment replicas. And now the mean steps per second has jumped to about 12,000. So there's almost a linear increase as we scale up the number of environments. Now, in comparison, we also tried this on CPU-based architectures with the same exact settings, and that ran only at about 500 steps per second. So using WarpDrive on the GPU, is giving us a 20x time throughput jump. And note that we only use 50 environment replicas, but we can even go higher. Memory is the only constraint of the GPU, and with that, we can get even higher steps per second. And that means essentially faster training. So overall, we have demoed that WarpDrive provides a complete end-to-end multi-agent training package. You can use your custom RL gym style environments integrated with WarpDrive with just a few lines of code. And just running it on GPU is many orders of magnitude faster steps per second compared to traditional CPU-based implementations. Now, again, all of this code is available in our open source repo, so please do check it out. Okay. Okay, so now we used WarpDrive to train our tag environments, and these are results that we see after training. So with WarpDrive, we were able to perform training on these 100 agents within just a few hours. And we used 3 different scenarios in which we performed training, each with a different runner to tagger speed ratio. For the figure on the left, the taggers were allowed to be twice as fast as the runners. And you can see that all the runners get caught really soon. For the figure in the center, the taggers and the runners had the same speeds, and the runners were all eventually caught, but sometimes even with the taggers cooperating and teaming up to catch them. For the figure on the right, the runners were twice as fast as the taggers, so it gets really hard for the taggers to catch all of them. But this does show that within just a few hours, you can start from scratch and train even complex environments using WarpDrive. So next, I'll hand over to Tian, who will talk about the building blocks of WarpDrive.
Okay, hello everyone. Let me give some details of the fundamental architecture design of WarpDrive. So as we know, a key feature of GPU is that GPU can manage, handle, and schedule many computational threads in parallel, and those threads are organized in blocks. WarpDrive basically fully utilizes this feature to achieve the maximum throughput. Next one, please. So within WarpDrive, each GPU thread simulates an agent. That means that each GPU thread will handle the end-to-end reinforcement learning rollout and talk to other agents. Next, please. So each GPU block will contain multiple threads and run a multi-agent simulation replica. Next. And in WarpDrive, it handles the shared GPU memory and store policy neural networks and batches of simulation data together. That means that in WarpDrive, we almost totally remove the communication cost between the CPU and the GPU. We also make the GPU memory access to be in place, meaning that we even remove the data copy within the GPU. So it's very efficient in terms of the data transfer and the communication. Next. So on the top level, we have a data manager and the function manager as the Python classes to define the GPU reinforcement learning workflows. We will get back to this detail later. Next. So this picture illustrates basically the bottom-up end-to-end workflow within WarpDrive. So basically, as I mentioned, we have each individual thread taking care of each agent in the reinforcement learning, and GPU blocks manage the environment and all those agents together. And meanwhile, the GPU device handles all the memory access and talk to those threads in place. On the top level, we have the CPU host implemented in Python as data managers and the function managers to manage all those internal device kernel functions. So next slide, please. So to execute this design architecture, we have the following code structure. Basically, WarpDrive consists of 4 main layers. The bottom layer is a CUDA layer, which contains a CUDA C version of the environment step, reset, sampler functions. So basically, the environment function is a CUDA C step function, and it takes care of basically the rollout, meaning that when agent receive a new action, it will change its own state and so on and so forth. We provide several different default environments for user to benchmark and test. And we also provide the customized environment data loader, so you can basically compile your own CUDA C environment, and the WarpDrive will automatically integrate and wrap up your environment into other CUDA C service functions that WarpDrive provides. So next, so so for the next layer is the API layer. We basically provide the CUDA function pointers and the data pointers for Python to access and control those CUDA backend. And going up, we have the Python service layer and the Python environment layer. Basically, they are some fundamental base classes, for example, environment class and the sampler class, to take care of the communication between the Python CPU host and the backend kernel functions seamlessly. So basically, from the user's perspective, we only need to play with those Python functions and Python classes, and we can control everything on the host level. And finally, we have the application layer that the user will mostly interact with. We provide, for example, the trainer class that Sunil just demonstrated, and we have the environment wrapper to wrap up the environment class, and the model is usually the PyTorch model. So with those model classes and the trainer and the environment wrapper classes, we can basically fully realize like a gym environment, for example, step function, the reset function, and connect with the trainer to train any reinforcement learning model, as we did from any other kind of open source or like RLib, so on and so forth, those kind of training workflows. So next one. So let me provide some code highlights. So as we mentioned, WarpDrive provides this environment class. For example, here we have a tag continuous class. Basically, WarpDrive supports and enforce gym API. That means we have the reset function and the step function. Next. And we also provide the DataFeed class that basically facilitates the user to define and push data into the GPU. So you can, for example, call this function get data dictionary and define your own environment, for example, some locations or any other features, and push into the GPU only once, because later on, WarpDrive will fully running everything exclusively inside the GPU without any talk to the CPU anymore, unless you want to look at the training result or get some checkpoint. Next one. So the most important part for WarpDrive is writing a step function. Means that, for example, when agent receives a new action and how it evolves its own or other agent states during this process. So WarpDrive supports both the Python implementation and the CUDA implementation. So usually we recommend to implement both, because usually a Python step function is easier to write. And once we finish the step function in Python, we can execute the CUDA step function counterpart to basically reproduce the same result. In order to make sure that both implementations are consistent, we also provide, I think that's the next slide, please. Oh, I will get back to how make these two versions of step function consistent. But once we have finished this step function, the WarpDrive can automatically wrap up this step function into the WarpDrive ecosystem. And if you turn on the use CUDA equal to true, then using the, for example, the data manager to push all the data once into the GPU, then the following is just a very convenient rollout step managed by the WarpDrive, and the CUDA step function will automatically run from end to end. So as I just mentioned, in order to make sure that this step function will be consistent between the CPU Python implementation and the CUDA C execution, we provide several convenient check toolboxes. For example, we can go to the next one. Yeah, we provide this CPU GPU environment checker. So you can run the CPU and the GPU version exactly for the exact same episode, and you can check whether the observation or reward are consistent between these two versions. So you can be very confident that your implementation is correct. Then you can wrap up your environment within the environment wrapper. So with GPU simulations, this environment wrapper will push the data only once from the CPU to the GPU. Then all the relevant data will be copied to the GPU, and later on all the reset will be reset within the GPUs, and the subsequent steps will happen also exclusively on the GPU as well. And we also provide end-to-end reinforcement training, as Sunil just showed. So yeah, I think I can hand over to Stephan to conclude. Thank you.
All right, thanks. So hopefully this talk has given you a quick overview, and you can see it as an invitation to check out our software. Everything is open source. So the high-level goal of this project is to democratize access to high-performance reinforcement learning systems. Especially in a multi-agent setting, there simply is almost no software out there that gives you high performance and that can be applied to complex multi-agent problems. So moving forward, we want to engage the community in expanding this WarpDrive framework. For instance, we want to add more simulation environments for the problems that you care about. We want to think about hybrid multi-GPU setups where each GPU can run this WarpDrive framework, but where the GPUs are working together as well. So we combine the best of both worlds of distributed reinforcement learning and of the WarpDrive approach. We also want to simplify building simulations that can run on a GPU. Currently, writing simulations in bare-bone CUDA C is still a bit complicated, more complicated than writing it in other high-level languages like Python. And so we want to see how we can integrate WarpDrive with tools that make it easier or create new tools. And finally, there are also tools that specifically focus on accelerating machine learning on GPUs, and we want to see if we can integrate WarpDrive with those as well. Next slide. So that's it for this talk. Hopefully this has made you excited to go check it out, to learn more about multi-agent reinforcement learning and what it can be used for, and how you can use WarpDrive for your machine learning problems. So check out our code on GitHub. There's also a blog post at this link in the middle. And also we have a white paper on arXiv with a lot more technical details if you're interested in learning more about how it all works under the hood. So thank you so much for listening.